Last time we kind of started building up kind of a common vocabulary, right? And we started building into this idea of you can draw circuits multiple ways, and some of them are more complicated than necessary. And I kind of went through the intuitive idea of this looks too complicated. Let's start talking about how to mathematically simplify things. How do we do this math, this Boolean algebra, right? And we start off with some identities that I've already started alluding to, right? So if I have a variable x and the OR operator, if I have x or 0, right? What's that going to do for us? It's just x, right? Because or 0, well, 0 is never true, so it's just x. Okay, so if I have x or 1, what do I get?
Just 1.
Just 1. It doesn't matter what x is, it's always true because the 1 is true. If either of them is true, it's true. X or x. Just x. Yeah, it doesn't, I mean, it's repeated. It's the same thing. All right, x or x bar. Yeah, because it's either this is true or that's true, because it's if it's 0 here, this is 1. 1 here, 0 there. But either case, we end up with 0 or 1, which is true. Okay, so those are like our simple identities. These are all on like page 31 that I'm going through. I'm not going to go through all of these. What we'll do is I'll make some assignment, like some homework assignments to go through and start practicing. And I will usually end up posting a video. And because we're a little bit short here today, I will certainly try at least to give you some more example problems to work through, because Boolean algebra can be hard to see what you're supposed to do. So lots of practice is what's needed. And we're going to be doing this kind of throughout the semester. So this is really kind of fundamental to what we're trying to accomplish. Okay, so some other important ones is that you can distribute. Right? Just like algebra, you can distribute, and you can go the other way, right? You can factor it out. There's this one that we call logic adjacency. Where if we have x and y or x and y bar, it just equals x. We can prove that
By factoring it out, right?
yes, just by factoring it and then using this identity. All right, so now we're going to go into everybody's, what ends up being your least favorite one, but very important. We call it De Morgan's theorem. And what De Morgan's theorem is essentially doing is hopefully I made this really clear. I know I did in my other classes lecture. Right, those two are not equal. Those are different. Did I cover this? Right, okay. So now that we established that, I can write this. We don't really like having a not over a larger expression. So De Morgan's theorem is really a tool to simplify this type of expression. And all it says is that if I invert each of the terms and flip ors to ands and ands to ors, I end up with an equivalent statement. So let's do it, right? So the or becomes an and the x and y each become x bar and y bar. Similarly, so X and Y, I flip ands to ors, I go back the other way. And each of those get a bar. So these two are what we call De Morgan's theorem. And I'll go over an example like right now of using De Morgan's theorem for simplification.
Can I ask real fast? So when you say invert then, what does that mean exactly?
Invert is the concept of zeros become ones, ones become zeros. In this case, we put a bar over the top saying not. So the inverse of x, so saying not x, is the inverse of x, which is equal to x bar. So if x is 1, the inverse of x is 0.
Okay.
So when the bar is above like both terms, it's like it's nodding the output of the operand, not.
Yes. So what it's doing, and sometimes I think this is really good to visualize, is if I'm saying this is not x and not y. This is not x and y. Right? Because here is x and y. This net is x and y. This inversion then is not x and y.
So if that was an OR gate, would that be equivalent to the one on top?
If this was an OR gate,
Yeah, if that was an OR gate, would that be equivalent to the one on top then?
not quite. So there is an equivalency that you can do, which is to say, well, first off, I mentioned that we can turn this into that. So when I'm drawing a bubble means an inversion.
Won't they draw bubbles on the input side as well?
Yes. So functional equivalency. So this is a NAND gate. There is an equivalent way to write this one. Here. Those are both NAND gates. But we're going to get to more of that later. This becomes more important next week, actually. So if you're curious if something is equal, what tool have I taught last time that we could go to check? Truth tables, yeah. So we go out and start drawing the truth tables of these various things to see what is equivalent. We could also use the Venn diagrams, right? Okay. Trying to remember how I got here. But yeah, example time. So let's say that I have the expression A, or it is going to be A bar, or B in parentheses, and CD bar. Okay. So this would be possible but obnoxious to draw the circuit for this. And it's probably not the simplest form. So what we want to do is use De Morgan's to simplify this. Now, what we don't want to do is think that so here I've inverted the terms x and y. For the case of De Morgan's, the terms that I need to invert are actually the higher level terms. So that and that. I can't jump down to inverting the A and flipping the and. I have to first deal with this and. So one and or operator at a time. Okay, so let's do that. It stays as A or B, but I bar that whole term. I say not that whole term, right? Because I'm inverting that term, this one, the whole thing. This and becomes an or. And then I now have C, D bar, but I'm flipping that term. I'm inverting that term to a double bar.
There's no bar.
A double bar is equivalent to no bar. That's saying not X is equal to X. X bar is equal to X. Okay. So if I say F is equal to that, F is equal to that. Now this term is good. We're happy here. But we still need to go ahead and keep simplifying this one because I still have a bar over multiple elements of this term. So let's do it. This is then equal to A bar and B bar, which is then just let me digest that moment for a moment. But does everyone follow that? So things to be careful for is don't start by just jumping straight to A bar and B or C, right? We can't do them all at the same time. Well, technically you can if you're really careful, but I recommend just doing it step by step. So this, again, will get used a lot and it will come back into play because what this actually ends up enabling us doing relates to your question about the NAND and OR gate alternate drawings. Is this actually is a tool that will allow you to change between NAND gates and NOR gates. Now, the reason that matters is a concept we'll talk about more next time, but NAND gates and NOR gates are something we call universal gates. And what this means is you can use a NOR gate and a NAND gate to build exclusively to build any circuit. You don't need any other type of gate if you're using it, because we all know it's cheaper to build something at scale. So most of your logic that you'll purchase, if you go out and buy like a memory, it will either be NAND flash or NOR flash. All of the logic will be contained within one type of gate because it is cheaper and more efficient to do it that way. So what we do is we come up with logic expressions and we will eventually learn to convert them to specifically NAND or NOR technologies because that's our target. Okay. So let's do something that is a bit more of a practical problem that can kind of take advantage of a fair chunk of what we've learned now. So let's start by saying, I want a circuit that is true if I have a 3-bit prime number. Okay, so I'm going to have an input of 3 bits, and the output is true if it's prime. Okay, so that sounds hard, right? Like, where do we start? There's an idea. Where do you think is a good place to start with that?
Truth table.
Truth table. Truth tables are a great place to start. So I specify 3 bits. We can count up from there. We'll go x0, x1, x2, and we'll call this P for prime. And then we have to draw out, right? We just have to count up to 2 to the n. There's going to be 2 to the n rows, where n is 3, so I'm going to have 8 rows. You could just count up in binary by going 0, 0, 0, 0, 0, 1. When I'm going quick, I like to use the trick and I recommend this on exams. Right? Ta-da, I don't have to know how to count in binary. I just created it. Okay, so we're going from 0 to 7. Now, I know not everyone's taken number theory and not everyone remembers their second grade math, so not prime, right? Is 2 prime. Yeah, 2 is prime. 3 prime. Yeah. 4, obviously not prime. 5, prime. 6, obviously not. 7 prime. Okay, so here is our truth table for prime numbers of 3 bits. If we added a 4th bit, we'd have to double the number of rows we have, right? Because it's 2 to the n. So now we're going to introduce a new vocabulary term. The term is a min term. A min term, and I'm going to read this exactly and then I'll clarify. So a min term is a logical expression that is true for one and only one row of the truth table. So min terms assume that you are writing out your truth table in order and you have an expression that is true for one and only one row. Okay, that doesn't sink in for a lot of people yet. Well, let's just draw it. Anywhere that I have a truth, I have a min term. That min term is this expression. Or in other words, here, I have not x2, yes, x1, not x0. Because it's associated with each of those terms. So go ahead and take just a moment to see if you, well, I'll do one more, right? So I like to start by just drawing out the 3 terms that I care about and then dealing with the nots after. So it's not x2, x1, x0. So go ahead and write the min terms for these 2 rows. Make sure you're understanding. Remember, I like to start by just drawing the 3 terms I need. Okay, someone from this side of the room.
X2, X1 not, X0.
Perfect. Someone else.
X2, X1, X0.
Perfect. Yep. Don't need to make any changes to that one. Did everyone get that? Perfect. Okay. So now what we can say is that prime, or P, new vocabulary term, is the sum of these products. Sum of products. Sum. Okay. So what that means is we're going to OR all of these terms together, all of the min terms together, because prime is true if this or this or this or this is true. So again, when I'm writing this expression, I just do this, 0, or x2, x1, x0, and I know I have 4 of these. And then I can go ahead and just fill in the nots for each of them. That's prime. This is a mathematical description of a circuit that will tell me if those three inputs are prime or not. This is not the simplest version of this. So now we can start using some of our simplification in order to simplify the circuit. Because if I was going to draw this circuit right now, what it would take is 4 3-input AND gates, where and then each of those would go into a 4-input OR gate, right? That's a big circuit. It is unnecessarily complicated. I'm gonna erase this, sorry. Good. Okay. Okay. So what we want to do is start looking for things that might simplify in this expression. Does anyone see something that could simplify?
So the first two terms, we can just write it as x2 not x1, because x0 is x not x4, and like the term changes, so we can just eliminate that and make it to one term.
Exactly. So he's using logic adjacency is a theorem, right? So if I have this term and that term, and they're ORed together, it doesn't matter what x0 is. Another way of doing that is the factorization. Oh wait, no, not on that. Yeah, so you could have x2, x1, right? So I've just pulled out the x2 bar, x1, and I'm left with this or that, which is always true. And if I have x and y, right? This is equivalent of saying x and y or y bar. Remember this theorem? Oh, sorry, 4. Y or y bar is 1, that's 1. If I have the term of x and 1, yeah, it's just x. So that simplification then, boom. These two terms condense down to just that. Over here, we're left with these two terms. Well, kind of looks like we have the same thing, right? But this time it's the x1s that's left. So in fact, factor out the x2 and the x0, drop the x1, and all I'm left with is no bars. And therefore, P sorry, I forgot that next one. Or, because they're still connected with or,
Question, so the only time that you can factor those out basically is if they are connected by the or. So those factors have to be, or can you do like the end term with this end term?
yeah, no, I could
And it's
absolutely.
all connected with ors?
So this one has the shared x1. I could try and like factor that out and do something with x2, x0. It wouldn't quite work out.
Just
Yeah.
theoretically, you can do it
Yeah.
with any of them like a normal math expression. It
Yeah.
doesn't have to be right next to each other.
Yes. Yeah, yeah, it is just algebra.
Okay.
So that's our expression, right? And so now instead of having 4 3-input AND gates into a 4-input OR gate, I have 2 2-input AND gates and 1 2-input OR gate, right? I've made that cheaper and less power hungry for essentially free, right? Just for a couple minutes of my time. Okay. Are we good if I erase this? Okay. So keeping this truth table then, you'll notice that it wouldn't exactly, it's not easy to write out that expression, especially if you start getting up to 4-bit, 5-bit, 6-bit min-term expressions. So there is a shortcut. We can just write that prime is equal to the sum of the min-terms. This is min-term 0, 1, 2. 3, 5, 7, right? This is the same expression as the this or this or this or this, but much shorter. But we can shrink it down even more, actually. It is also equal to the sum of min-terms two, 3, 5, and 7. So I could ask you a question that said, please simplify the logical expression for P and then just give you this. When I do that, I am providing you all of this information in just one line. When you start out, you're going to have to almost certainly draw out the truth table and then figure out what those are. But once you kind of used to the idea of it, you'll just have a simple cheat sheet that you can just go through and see, because that min-term 2 never changes. It's always the same. Okay, so then there's this other idea where you can have the product of sums. So this is the sum of products, and there is also a product of sums. So you're going to explore this in the homework. I don't think this one, but probably next week's homework. So I'm not going to go too into it because I kind of want you guys to walk through it, but I want you to be familiar with it. And all a product of sums is doing would be something like this, right? So the product is here, the product of two sums. And you could continue, right? It could be a third sum. So that would be a POS, product of sums expression. Similarly, there is another term, and I think it might be a homework assignment to do the conversion. But another idea here is, what if I care about the zeros instead of the ones? Well, then I can write out the max terms. So what the max terms say is that it's 0 for a given row. The way I would express that is P is equal to, and we don't use that sum signal, we use this sum max of everything that isn't this. So it's 0, 1, 4, 6. Did I miss one? Nope, we're good. Now a max term isn't quite just the and. And unfortunately, I think I screwed this up with my other lecture, and I'll have to go back and correct them. But what you're looking at is we want P to be true when these are true. So let's look at one example. So this is 0, 0, 0, right? So that max term is but that's 0, right? We don't like 0. We're not saying prime is 0. So there's actually two ways that you could do this. You could say not prime is equal to that. Or we can use De Morgan's. And we put the bar over here, right? So prime is true when we don't have x2, x1, x0. Or the other ones. Then we use De Morgan's, right? And there's more to the expression. And now, or, so each of these, the ands become ors. We get double bars on all of them, so they just flip. And then P has to become not all of that. So this and is going to become, or this or is going to become an and. And you're going to end up with an expression like this, where the product of sums is the or of all of your, let me make sure I say this correctly, the or operator of all the inverted terms. So the term should be x2 bar. When we invert the term, or them together via De Morgan's, they all get anded. It's equivalent expression. These two are equal, but you write them a different way. Yeah.
So when we know the difference to use either one? Depends on what we need as a result.
Excellent question. I will happily give you a sneak peek to answer that question. Are we good if I erase this? Okay. So let's say that I ask you, because right, this idea of universal gates, I want you to design a circuit that detects a prime number using only, let's say, NAND gates, not AND gates. Sounds hard, right? But it turns out that if you draw it as a sum of products, it becomes simple. Why? Well, let's do a theoretical one. So this is what all sum of products look like, right? AND gates into an OR gate. Now, a NAND gate. I want you to design this using a NAND gate. NAND gates look like this, which is equal to, well, I guess equivalent to this, right? Well, what do we see? Or and. So again, what happens if I not something, right? It stays the same. Not X is X. So we call this bubble pushing, where I'm just going to take two bubbles and put them right here, because not doesn't change it. And then I'm going to push one bubble along this wire until it runs into the next gate. Okay, so a bubble goes here. Put another bubble, push, 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 push. Rinse and repeat for each of the traces. It's all NAND gates. Just took a circuit from OR gates and AND gates and turned it into NAND gates. If I were to tell you I want a circuit made entirely out of NOR gates, and you started with a product of, or you started with the sum of products, it would be really hard. But if I said I wanted NOR gates, and you started with a product of sums, same procedure. Because a NOR gate is this, which is equivalent to So that's why you would use one or the other. There are other reasons, really. As designers, we tend to stick to the sum of products because it's easier. And we'll see more why in, I think, 2 weeks. We're going to learn another tool called K-maps or Karnaugh maps that will, again, come back to product of sum of products. This idea is important, as is the ability to express them and understand that when I write sum of 3, 4, right, it makes sense to you. Okay. Okay, so, right, hopefully everyone has this book. If you haven't got the book yet, you don't need the CD-ROM. You can buy like a used one without the CD-ROM. You can also use a second edition if that's all you can find, or it's crazy cheaper. But you would have to get the homework assignments that use the book from someone else. Just ask what the questions are. Here I'm going to be doing an example 2.1 on page 33. Just to do some more of the Boolean algebra simplification, because I think seeing examples is helpful to start being able to see where we can find simplifications. Okay, so what they want to do is they want us to prove that the following two expressions are equal. Sorry, writing while I look at a book is never a skill I've yet developed. So what they want us to do, and I'm going to make sure that this is correct. And if I ever do something like really weird, I do get stuff wrong up here. I'm not going to be embarrassed if you like call me out on it. And don't be afraid if you're confused, just be like, hey, is this true? Because it could be you confused, or it could be making a mistake. And I don't want everyone to sit out there going like, what is he doing, when I'm the one that made the mistake. So don't be afraid of asking. Okay. All right. So we want to prove that these two are equal. Now you can go from either side, right? You could try and make this side look like that side, or vice versa. Going from here to here is probably a little bit difficult because you're going to have to create more terms. So what we're going to do instead is, well, let's see. I want to see what they do, because that's probably not how I would do it. Okay, yeah. So they're basically going to, what I would do, FOIL, right? From algebra, first, outside, inside, last. They still teach that, I assume. They do it a little bit shorthanded. So they're going to say x1 or x3 gets multiplied with x1. And then the x1 or x3 gets multiplied with x3 bar. Right, so instead of doing the full FOIL, they kind of halved it. If you were to do the full FOIL, x1, well, let's just do it. Don't write squared, right? Let's stick to x1, x1.
Wait, isn't that X1 have a bar on it?
Oh,
Yeah.
there you go. Oh.
And then the first and last terms just become one, right?
Which two?
Means zero. Those two are zero, right?
Yeah,
The
so
first and last one are zero.
yeah, x1 bar via one of our identities is just 0, right? Because that can never be true. This one can never be true. And then we have, hopefully, the answer. Yeah, right? Because these two are those two. Don't do what I did and accidentally forget a bar on an exam because it gets complicated, right? Exam questions are usually designed to simplify pretty neatly, and then when you forget a bar, you get really lost. Okay, good if I erase this and move on to the next example. All right, next example. Let's go ahead and say they want this is example 2.2 on page 34. Let me step back and make sure I did that right. Okay. So it's usually good if you get a question like this that is saying prove that two things are equivalent, right? To look at both sides and see if you can see what might be simplified. What do we see as a noticeable difference between the left-hand and right-hand side?
There's no X3.
There's no x3. So that's a hint that we're trying to figure out why does x3 just go away, right? So let's look. Well, x3 is in all of these terms. We have two x3 bars and two x3s. Well, let's start thinking about logic adjacency, right? They're x1 and x3 bar and x1 and x3 no bar. What does that simplify to? x1. So this term, that term, that's probably not a good way of doing it actually, right? I was thinking of using x's to mark which one I was done with, but that's a lot of x's. So a check mark, let's go with a check mark. Okay, now here, x2 bar, x3 bar, no bar on the x3. What do we get? x2 bar. Another question is, did I do something wrong?
Then a right hand could be simplified as well.
Probably.
We can do the same thing on the other.
x2 bar, x2 bar, x1, x1, x2 bar. That's an interesting one, isn't it? There is, I believe, a theorem for that. And if there's not, this book is. Last book I used skipped this theorem too, but I like it. Page 31 was the theorem.
Question, why is there the x2 bar or x1, x2?
So this guy and this guy are, I won't skip that one. So I have x2 bar.
And then the others cancel out.
Is a way to rewrite that. And then once I have this, it's always 1. So that's x2 bar or x1, x2. I really not have that one either. I love this expression. All right, well, they don't give us this identity. Can we prove it? What tool do we have? A truth table. Actually, this is really good. I haven't shown you this type. So we have x1, x2. I generally count up my x's going this way. And then the expression that I'm evaluating is x1 or x2 bar. So I have to have x1 is true or not x2. That one. All right. So what I did is I just identified that I started with the x1 because it's an or statement. So if either of these two conditions are true, this is true. So I just went, okay, well, x1 is 1 here and here, and x2 is 0 here and here. Those two, this is 0. Okay. Now this one's a little bit trickier. And we say something like, okay, so we need either of these two. So let's start with the simpler one, just to get the ones filled in. Not x2 is this one and that one. Okay, that's looking good. Or x1 and x2. Well, that's not the case here, but is the case here. Right? So our truth table shows that we didn't make a mistake. They look very different, but you can't actually simplify. The last book I used didn't put this theorem in there, and neither did this one, which is bothersome, because this comes up a lot, saying that this is equal to that. Right? That's what we just proved with these truth tables. So then we can generalize that to make it a little more perhaps clear, and say, well, we'll call this X and this, we'll call X2 X, and we'll call X1 Y. And in fact, to make it easier, we will call X2 bar Y. We're going to call this Y. Or sorry, we'll call X2 just X and X1 Y. So what that is saying then, if we have X or X bar Y is equal to X or Y. That's another theorem that it doesn't look like is explicitly in your book that you will find helpful.
Oh, I think it is in the book.
Oh, is it?
Yeah, it's like 16A on page 30.
Oh, there it is. Yes, thank you. Okay, page 33, 16A. It has a 16B that is, I actually don't use that one as often, but it just states 16B is X bar or Y is equal to XY. So now remember, my exams are open notes, open book, open internet. Now, there are probably, I haven't checked, online like logic solvers. You're still going to have to go through and show all of the work. So the points come from showing the work. So sometimes you're going to either put something in, it's going to spew out an answer. First off, be skeptical of the answer because algorithms that simplify algebra don't do so the same way humans do it, and you can end up with wrong answers, essentially, that aren't really the most simplified. The short version of it is there's this idea of local minima. So it'll start simplifying and go, okay, if I do anything else to this, it gets more complicated. And it'll get stuck there. Whereas you and I would know that, no, we can actually get more simple. This would be actually a really good example of something where a computer algorithm might get stuck. Because to simplify from here to here, you actually have to make this one more complicated first, and then to get to there. So you can get stuck in local minima when you're trying to prove stuff. So make sure that you can do the steps, but the main takeaway is you don't have to memorize all of these theorems. What you have to do is be acquainted with these theorems so that when you're given these questions, these problems, you can see how to simplify, how to move forward, and you don't have to go through line by line of each of the theorems. You can have on a little cheat sheet of going like, not that one, not right. I want you to speed it up by understanding some of the more important ones. I've only got a couple minutes left, so I will leave us off with a little bit of a teaser for what kind of comes next. Oh, and I do want to say in this class, you'll notice I use announcements a lot. So do pay attention to the announcements. I use them a lot. Okay, so what we're going to start building up to next is just kind of an in-depth look of I've been drawing, right, an AND gate. And we've been talking about, oh, well, this is a circuit. What we're going to build up to is what is inside of that AND gate? Really, what is it made out of? Physically, when it's on a chip, how do we build it? And that's what we'll get to next time. So we do have a couple minutes. If you guys have any questions, I can answer them. If otherwise, enjoy the rest of your day.
There's no class Monday, right?
Is it Martin Luther King Day? Or, yeah, there won't be class.
The first lab will be a week from this Monday.
Oh, that's rough. Yeah, I guess so. Yeah, we'll get there. I'll make it work with the labs. I'll have to double check the schedule, like just look at the Weber schedule, and as long as it is an official Weber state holiday, I don't 100% know what dates that things are, so, okay, yeah. I don't want to be like, yeah, it's a holiday, and then you guys miss, yeah.
Are you the teacher for the lab or?
Yes, I do the lab as well.